All right, so up until this point, we've kind of left out trigonomic functions as we talked about derivatives, and that's not really all that fair. We should be nice to our trig friends. So when we're trying to talk about these derivatives for trig functions, it helps to understand some special limits that come into play when we're talking about trig functions. So both of these are going to be given to us by the squeeze theorem. We're not going to talk a whole lot about it. And these two limits say that if we have the limit as some theta approaches 0 of sine of theta over theta, then this is going to end up equaling 1. Note that it ends up being the same if we looked at the limit as theta approaches 0 of theta over the sine of theta. In either event, we end up getting 1 as a result. So when we're talking about theta here, theta is just a placeholder for something. It doesn't necessarily have to be an angle. It could be whatever we decide x is that day. And so that is something we want to make sure we keep in mind, no matter what our variable is. The important thing is that it matches. So if I've got theta here, it has to be the exact same theta here. We'll come into that in the first example. The other thing we'll see that the squeeze theorem gives us is that the limit as theta approaches 0 of 1 minus cosine of theta over theta ends up being 0. So again, both of these, or all three of these, if you like to think of these two as separate, come to us from the squeeze theorem. Okay, so let's go through some examples involving limits with trig functions then. So if we wanted to find the limit as h approaches 0 of 1 minus 2 cosine, or 1 minus cosine of 2h over h, what we get here is 0 over 0. If we plug in 0 for h, we end up getting 1 for cosine of 0. And so 1 minus 1 is 0, and in the bottom we'd have 0. So this is a 0 over 0. And so what we want is we want this to match what's inside here in order for us to be able to go ahead and apply this. So what we're going to do is we're going to multiply the numerator and the denominator by 2. And so what this gives us then is the limit as h approaches 0 of 2 times 1 minus cosine of 2h over 2h. And so now just looking at this part here, and thinking of this whole thing as being multiplied by 2, we can pull the 2 out of the limit, and then that gives us 2 times the limit as h approaches 0 of 1 minus cosine of 2h over 2h, and now this and this match, and so we can apply this limit here, and we'll get 2 times 0, which is just going to be 0. All right, let's look at another example of a trig limit we could do. So if we wanted to find the tangent of 4t divided by t times the secant of t, this ends up giving us another example of 0 over 0, and you can see that for yourself. So what we want to do is we want to kind of think about this as being in terms of sines and cosines, because those are the things that we have these special trig limits for. So we can think about this as being the limit as t approaches 0. Now tangent is going to be sine over cosine, so in the numerator we'll get sine of 4t divided by cosine of 4t. This is our numerator fraction. And in the denominator, secant is 1 over cosine, and so we'll get t over cosine of t. Now, if you're dividing two fractions, you can go ahead and rewrite this by multiplying by the reciprocal. And so this is the same as the limit as t approaches 0 of sine of 4t over cosine of 4t times cosine of t over t. Okay, so how does this help us? Well, one of the things we know is that we can use this nice thing with the sines if the angles match. So in order for us to get that, we would want the 4t here to match some sort of 4t out here. Now, unfortunately, we don't have a 4t, so what we're going to do is we're going to multiply top and bottom by 4. So this will give us the limit as t approaches 0 of 4, I'm going to rewrite it a little bit, cosine of t times the sine of 4t over the cosine of 4t over 4t. So again, we multiply the numerator and the denominator by a 4. And so in doing so, this part of the limit we see will become 1. And so this will just be the limit as t approaches 0 of 4 cosine of t over cosine of 4t, and then times the limit as t approaches 0 of sine of 4t over 4t. So we can remove the limit. And so this limit will become 1. And when we go to plug in 0 for t, we get 4 cosine of 0 over the cosine of 0 times 1. So remember that cosine of 0 is 1, so it's okay for us to then cancel these out. And so we'll just get 4 times 1, or 4. Man, all these really complicated limits, and we're getting these kind of mundane answers. On one hand, it's kind of nice. On the other hand, I'm sure it's also kind of like, what? What's going on? All right, let's go ahead and try to evaluate the limit as t approaches 0 of sine squared times 1 minus cosine of t divided by 4t cubed. So, again, if we go ahead and plug in 0 directly, we get 0 over 0. Not all that great. What we can do is we can break this up. So we get the limit as t approaches 0 of sine t times sine of t times 1 minus cosine of t. So remember, the reason we can do this is because sine squared is just sine times sine. And then divided by, if we're looking at 4t cubed, well, that's just 4t times t times t. Okay, so what does that mean for us? Well, it means that if we look at grouping this together and this together, these both go to 1 as t goes to 0. And here, when we look at this, this goes to 0. So what does that mean? Well, it means when we go ahead and apply our limit to each of those individual pieces, we get 1 over 4 times 1 times 0, or just 0. All right, so what does all this have to do with the derivatives? Well, we know that when we're trying to find the derivatives, we end up getting things where we have to go ahead and do limits. I'm actually just going to show you the derivative rules, and we're only going to talk through how we get one of those the hard way. So when we have our trigonometric functions, the main two to always know, because they make up all these other ones, are sine and cosine. So sine's derivative, the derivative of sine, is cosine of x. And the derivative of cosine ends up being negative sine of x. What's kind of cool about this is it kind of creates a little bit of a loop. So if you've got sine, the derivative of sine is cosine. Well, the derivative of cosine is negative sine. Well, negative sine's derivative then would be negative cosine, and the derivative of negative cosine would go back to being sine. So you kind of get a nice little loop going on here of all these things. Remember, tangent is just sine over cosine, so you could use these to try to go ahead and find the derivative and use a little bit of quotient rule. However, we're going to find in the end that it ends up being secant squared of x, which is the same as secant of x whole thing squared. If we talk about the cotangent, the derivative of cotangent is negative cosecant squared of x. And again, you can rewrite this the same way you write the secant squared. And then the derivative of secant ends up being secant of x times the tangent of x. and the cosecant ends up having its derivative be negative cosecant of x times the cotangent of x. One of the things to note is that all these ones that start with cosine, cotangent, cosecant end up having derivatives that end up being negative. All the ones that don't have them end up being positive, which is kind of neat. But again, you're probably most important two are these two, because if you know how all the other trig functions work, and you know how to use your quotient rule, you can find all of these by knowing these two. It might take a little bit more time, so you might find it useful to memorize them, but these are the main two you should know. So I guess the question ends up being, why is it that the derivative of sine is cosine? Well, from a graphical standpoint, here's sine, and here's cosine. So this is y equals sine of x, and here's y equals cosine of x. And so when we look, everywhere we have sine starts at 0 and it goes up and it increases for a while, and while it's increasing until it gets to pi over 2, its derivative would be positive, and it gets less positive as we go. And then when we get to pi over 2, it starts to actually become negative, which is where we start looking at cosine, and it starts to go down. Then when we get to pi, we slowly are going down less quickly until we bottom out at 3 pi over 2, where we get another 0. And then we start going back up on our way to 2 pi, and so our derivative should be positive. So it kind of just flows pretty naturally. Now from an algebraic standpoint, if we wanted to go ahead and find the derivative of f of x equals sine of x, our derivative of sine of x is going to be found by taking the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is the limit as h approaches 0 of sine of x plus h minus sine of x all over h. Now there is a trig identity that gets used here. So if we consider this to be our angle u and this to be our angle v, there's a trig identity we get to use. So if you don't remember these trig identities, do not worry, you're not being tested on them. This useful trig identity says that the sine of u minus the sine of v equals 2 sine of u minus v over 2 times the cosine of u plus v over 2. It's kind of a weird formula, but if we try to apply it here, what we'll get is the limit as h approaches 0 of 2 times the sine of x plus h minus x over 2 times the cosine of x plus h plus x over 2 all over h. And so now, if we take this and simplify it, the limit as h approaches 0 of 2 sine, we take x minus x, we're just going to get 0, and so this will just end up being h over 2. And if we look at this, this will be cosine of 2x plus h over 2 all over h. Now from here, what we're going to do is we're going to rewrite this 2 as dividing by a half. So instead of 2, we're going to write it as times 1/2 in the denominator. And so now we have h over 2 and h over 2. And this allows us to use the identity we had from above, where we get to say that we have the limit as h approaches 0 of sine of h over 2 over h over 2 times the limit as h approaches 0 of the cosine of 2x plus h over 2. And so when we let all these go to zeros happen, this, using our identity, will just become 1, and this will become the cosine of 2x plus 0 over 2. So if we add 0 and we don't really think about the 0 part, we have the cosine of 2x over 2, which will just simplify to the cosine of x. So if you happen to know the trig derivative and you know this nice limit function, you can get all the way to finding that the derivative of sine is cosine on your own. Is this something I'm expecting you to know how to do on a test? Absolutely not. Is it kind of cool? Yeah, it's kind of cool.